So welcome to the Akka no Zen talk, so the Zen of Akka. This talk I actually prepared for a Japanese conference, and I figured it's gonna be fun if I leave the Japanese subtitles so you can learn a bit Japanese as well. But enough about that. So I work at TypeSafe, which is actually in the middle of having a rename, a rebrand. So on Monday there's gonna be an announcement, so we're gonna have a new name. You can make lots of jokes about the new name then. So I work on the Akka team there, and I also did a bunch of stuff about the reactive streams initiative. So if you hear anything about reactive streams or you want to talk about it, I'm here and available. So a bunch of stuff that I also either host or co-organize. So I'm also program committee at Java 1 in San Francisco and in Krakow, most notably the Geekon conference. And some community things. Okay, so that's enough about me. That's some customers, some example projects using Akka. And yeah, so I just want a quick show of hands. Who is using Akka? Oh really, okay. So you're in the right talk, I think. Because the talk is structured as a top, 14 or so tips of what I see people doing wrong. And maybe this talk will help you not to do the wrong things. So, the talk again is titled slightly after the Tower of Programming. So there's another one called the Zen of Programming. If you've seen the books, it's like a short story about the Zen master trying to teach his student about programming. So it's kind of hilarious. Usual quotes would be, "Without the wind, the grass does not move. Without software, hardware is useless." So quotes like that. So I thought, let's try to do it in the same vibe. So what is the Akka landscape? For those of you who have no idea what Akka is, etc., Akka is a toolkit. So that's one important thing, and I have another dot about it later. But it's not a framework. Sometimes people say the Akka framework. I tend to disagree because you really can just pick small pieces of Akka, and then you just pick this one small piece. So it's more like a toolbox, and you pick the one specific tool. You pick the hammer, or you pick the screwdriver. In our terms, this means you pick, for example, Akka actor, so that's the concurrency and distribution module, or I/O, which is for talking TCP, UDP, those kinds of things. And then the other modules are layered on top of it. So of course, the cluster is basically distributed actors. And then the other modules like persistence and typed. So, first rule is that one actor is no actor. So if you're trying to implement something in idiomatic actor style, and you have one actor, that's kind of missing the point, because one actor by itself is seemingly single-threaded, right? It's not just a single thread, it's jumping across threads, but semantically speaking, it's as if someone would be processing something on one thread. So what can it do with a message? So it can reply to a message, it can drop the message, so ignore it, or it can schedule another message to itself. The other behaviors actors can expose are change its behavior, right, and spawn child actors. And that's the complete API and model of what an actor is. So when you have one actor, you're not really using the parallelism or the concurrency that actors give you. So usually you have more actors. So for example, you have a yellow specialist Bob, and if you have yellow messages, you can ask the yellow specialist to do the yellow things. And already here there starts to be some interesting interaction, because the yellow specialist and your actor can run in parallel, right? So you start getting some parallelism out of your system. But then you can have a worker pool, etc., etc., and suddenly some patterns start to emerge from the design and the interactions of actors. So once you have more than one actor, you can do interesting stuff with actors. For example, instead of replying all the way, like from this guy to this guy to this guy to the original sender, you can use a pattern called direct reply, right? This isn't really nothing groundbreaking, but once you think about it explicitly, that hey, I could save some message sends if I only were to reply directly, well, it's going to be a better system. Okay, so actors are meant to work together. And when you model a system using actors, you basically can think about human interactions. So if I should be replying to someone, I should be first introduced to that person, right? So in code terms, it means I should get a reference to that actor, right? I should not be using actor selection. So actor selection is something that just by the path and the name of the actor, we can find a reference to it. But this is more or less like knowing someone's address and breaking into their house, right? You shouldn't be doing that most of the time. You should get introduced to that person and then use the reference to communicate with it. So avoid actor selection. That's the first step. Okay, so structuring actors. So when you first try to design something using actors, it sometimes looks like this. So a huge mess of multicolored, by color I mean classes here, right, types. And they kind of communicate all together with each other, and it's a bit of a mess. So instead what you should be doing when designing anything with actors really is to have a hierarchy. And by hierarchy I here mean, for example, the arrow here indicating that it's a parent-child relationship. So this could be just simply that the blue guys have some worker pools and they don't really do the work themselves, they just delegate it to the green guys. And if it's some heavy computation, there's going to be maybe another one at the bottom handling the heavy computation. So in code, this is simply a difference of, instead of system actor off, so system actor off does this mess, so everybody is on the top level. But when you use context actor off, it introduces the child relationship. So prefer always to do context actor off to have a nice hierarchy. And of course then new patterns emerge, so it could be a pool that is dynamically scaling, but the concept is the same, that it's structured. Okay, so once you have more actors, you probably should name them. And if you don't name them, this is how it looks. So if you just say context actor off, some props, this is the default names that are generated. So $A, $B, etc. And the algorithm we use for that one is basically just base 64 of a sequence number of a number of children of a given process, right? So you see A is 1, B is 2, etc. So why do we use that? For one thing, it's really fast to generate names like that, right? And by default, the default name can't really have information about the domain, right? Because we're just the tool and we have some names, but they're not useful to you as someone designing a system. So here's what you should be doing instead. So each actor can have a name and it should have a proper name, right? So it's very easy in the API, you just say, instead of just props, you also pass in a name afterwards. And here's one pattern that sometimes is useful. So you can basically have a incremental range of names, right? So if it's some kind of fetch worker, versus the first one, versus the second one, and at least then when looking at logs or trying to analyze the system, some printouts, then you see, oh, okay, it's the same type of actor, it's some fetch worker, right? So we actually have a utility for that, but we're trying to not expose it to anyone for reasons, well, you can write it yourself, it's 3 lines, and the rest is just sugar. But the other reason is because we don't really want to encourage that pattern, because it's not that useful. It's already better than no names, right? It's better than anonymous actors, but what you really should be doing is try to name them in a way that makes sense in your domain, right? So for example, if my actor is responsible of fetching videos from YouTube or Vimeo, then it could be encoded in the name, and only for the reason of debugging and understanding the system. It doesn't really change semantics in any way, right? It's just a name. But it really helps in a real system when things blow up and then you can see in the logs, even when you forgot to make a proper log statement about it, then at least you know, oh, the guy fetching this video blew up, or something like that. So this is why we don't really encourage just numbers in the names. you really should be thinking about what can be a good name. Okay. Another place where this is actually visible is in supervision. So supervision is the mechanism if a child actor blows up, so it throws an exception, for example. The parent, so the supervisor, gets this message that says what exception it was, and then you can, for example, log or do some side effecting thingies. And here the sender of that error is that actor that failed, right? So you can have the name again and have a nice error message if you want to. Okay, a small derail here. So there's two ways you can do interpolation in log statements. So there's the bad way, which is the Scala way. So the Scala way is to use the string interpolator. And then you can just say $ and a variable name, right? So that's pretty cool and nice, but it always will generate the string, right? And it will always concatenate the string, etc. However, if you use this pattern of having the placeholders, then it won't even build the string if if you don't have debug enabled. And everybody knows about it on the JVM that this is better, but sometimes people, when they start writing Scala code, they notice, oh, there's the string interpolator, and they want to use it everywhere. Well, you don't really want to use it everywhere, just in the places where it makes sense, not in logging. Okay, the fourth point is the matrix of mutability. You may have seen that one if you've seen any of Jamie Allen's talks, so there's a colleague from TypeSafe, and he has this nice way of explaining which references and which data types you should be using and which not. I thought that it's important enough to give it a nice visualization. So if you have a value, right, and it's immutable, that's basically the best thing that can happen because nothing can really change, but it's also not very useful because you can't mutate it at all, right? So it's a fact. It can be, for example, something that never changes, a fact. So then the other way is to have a variable with an immutable data structure, and that's actually where you want to be most of the time, because even if you send that object to someone else, someone cannot mutate it, right? Because it's an immutable data structure, and if you want to change the values inside the list, for example, you just get a new list that is, again, safe to propagate to other threads. So that's fine. You really shouldn't be doing the other way around, so have a value with a mutable data structure. For reasons I just explained, but just the opposite. Because if you accidentally leak that in a message to someone else, then that someone else could start mutating the list, and you really probably don't want that, right? You want to give out immutable views of your data structure. And then there's the last one, which please don't use it anywhere. So it's both an immutable collection in a mutable reference. So this doesn't make any sense because which way you want to mutate it? Do you want to swap the data structure each time you update it, like a variable kind of indicates, but at the same time it's mutable, so someone could be poking in it. So please don't use mutables with var. In code, it's very simple to find it, so it's a var and there's a mutable something. So if you see this anywhere in a code base, just decide if you want to be on this side or if you want to be on this side. Right? Easy enough. And you'd be surprised how many code bases I see with this mix. So it's a real problem, sadly. Okay. So next topic is blocking. So many of you raised your hand that, yeah, you were using Akka. Then you probably know the slogan or motto of never block, right? We kind of tell it to everyone. And we kind of mean it, but not in the sense that you may think we do. So this is a slide from last year's talk about the need for async. And this is the first and last reused slide from another talk. But I wanted to use it to highlight what blocking really is. So blocking is if you're basically wasting everyone's time because you did a call and you're waiting for it to return. Instead, you could be just doing something here during that gray timeline, but you're not. So that's blocking. So blocking is bad because instead of doing something useful, you do nothing. So let's not do that. So sometimes people write code like this because we want to benchmark Akka, for example. They want to benchmark Akka HTTP in this case. So they write a sleep in a future in a Akka HTTP route in this example. And then the question is, blocking in a future blocks the server. Well, yes, blocking blocks. But it's not really a bad question. Because the guy just wanted to benchmark something that, yeah, I'm doing something in my code, so I'll just simulate it by putting a sleep inside there. So it's not really a very bad question, it's just a bad way to simulate trying to do any work. So the problem here is that in a code like that, and with the default system dispatcher used by the future here, this is how the threads look like. So this bluish thing, turquoise, I think, is the threads sleeping, and the orange thing, orange state, is the threads just waiting and doing nothing. And if you didn't notice, this is where the application is actually doing something, right? So, yeah, here. So, great benchmark. It's mostly sleeping and then doing something in 1 second or so. So, I can of course tell to the guy, well, you're blocking, you're stupid, but that's not very helpful. So let's try to see what a helpful answer is in this case. So, whenever we say never block, we actually don't mean that. We only mean try not to block, and really, if you have to, then do this instead, right? So don't just arbitrarily, randomly block everywhere, just isolate it. So in the docs, we have a section about blocking needs careful management. If you need more details about it, go to the docs. But this is what we mean. So instead of blocking arbitrarily on the default dispatcher, which everybody uses, you can have a dispatcher that is backed by a thread pool, and backed by a thread pool of 16 threads. So this means we pre-allocate 16 threads, and they will be used for the blocking operations. So the only difference you need to do to the code base to start using that dispatcher for the blocking operations instead of the default one is, instead of saying system dispatcher, you say system dispatchers lookup and by name, right? So this takes it from the configuration, and then via the implicit value, it gets used by the future here. And this is how the threads behave then. So you see here we have an I/O dispatcher here, but that's unrelated to the ones we configured, right? That's one always spinning and reading from the TCP sockets, right? We just see it here because of a screenshot. And here we see the default dispatcher, and it's doing a little bit of work sometimes. The little bit of work in this code example is actually the routing infrastructure. So request comes in, and we need to decide, okay, which part of the route it should be dispatched to. So that's still on the default dispatcher. And here we have my blocking dispatcher, and you see all the sleeping is happening on this one, not on the default one. So you're not killing the entire system, you're just killing the blocking dispatcher, which is fine. So the never block mantra sounds cool because it's, yeah, never block, but it's not very helpful. The actually helpful mantra is blocking needs careful management, right? So whenever you have any kind of blocking or I/O operations trying to write to a file inside an actor, always apply this pattern, otherwise you're gonna suffer from performance problems. Okay, here's a similar one about awaiting, right? So await is actually a bit smarter than just blocking. It uses something that's called managed blocking. So managed blocking is something in Scala, when you use the blocking word, it actually uses a, again, dedicated dispatcher to do all the blocking, but it's still bad. If you can do something better, just do something better and not the blocking thing. So this sometimes appears when people for the first time try to write something with futures in Scala. And then they think, okay, yeah, I get this value back, I get the things back, so I need to wait for the result, and once I get the result, I can do something with it, right? Usual sequential step-by-step code. So that's not very good because, well, each time we're blocking and awaiting here, right? Oh, it's too small? Okay. So I'll be zooming in then. Yeah, so that's bad because you're awaiting all the time again, right? What you can do better, of course, not very, I mean, everybody should know that, is monadic composition of futures, right? So this is just sugar, but it basically, each time you see the left arrow, that's a flat map, right? So just once the future completes, I will be doing this other thing. And this doesn't await, it just, schedules something to be executed if the future completes. And then you get this cascade of the futures completing the thing. So there's one difference in these two codes though, because here on the upper one, we had this upper limit of how much we're gonna wait, otherwise, well, we just fail, right? On the below one, there's no timeout at all. We just said, well, if it completes, when it completes, do the thing. So in order to get the same semantics out of that code base is we kind of need to fail after the 3 seconds, right? To get more or less the same semantics as the above one. Here we had it in 2 places, right? First awaiting 3 seconds and then awaiting 3 seconds. So at a max, you could be waiting almost 6 in total, right? Almost, because just before the timeout triggers. But let's do just the 3 seconds in total for the entire pipeline. So in Akka we have a pattern that basically does that. So it's called Akka pattern after. And it says after 3 seconds, do this code block. And the code block takes a future, and it basically, after 3 seconds, will return that future. In this case, it's a failed one, so we simulated a timeout exception here. And then, in order to kind of bind it together with a happy path, we use the future first completed off, right? And completed also includes failed, so if it fails first, then we got the timeout instead of happy path. The usual question I get about futures is, why can we not cancel futures? Because JVM, I'm sorry. Okay. Serialization. So that's a turtle. If you don't get the hint, then yes, it's really slow. Specifically, Java serialization is really slow. And the problem with Java serialization is that we still have it as a default. We will actually remove that default in a future version, probably Akka 3. But for now, it still is the default. So why did we ever decide that this may have been a good idea? So sadly, it's very convenient, right? It just works. You just give it any object, and it usually, most of the time, just does the right thing and serializes it. It does it very slow and very bloated, but it does it. And the other ones, for example, Cryo or Protobuf, they actually require more work from the user to do the serialization. It's not, you say, well, now I'm going to use Protobuf and that solves the problem. You actually need to do some coding. So that's not a nice default to force everyone into doing a lot of coding to write a hello world example. So that was our reasoning to have the default Java serialization. Now the problem is people don't change the default once they go to production, and then they claim, ooh, Akka is so slow. Well, it's not Akka that is slow, it's like 90% of your time is being spent in Java serialization. That is slow. So where does this actually appear? So the serialization impact in the ping pong case. So ping pong case is when you have 2 actors and they send each other the same message back and forth, right? So this doesn't happen when you're in the same process, in the same JVM, right? We don't serialize them there because why would we? But once you hit the network, so you have 2 nodes communicating, there's going to be the serialization overhead. So there's more work, there's going to be bigger latencies, so there's going to be decreased throughput. So you want to have serialization as fast as possible once you go, in a real deployment that has multiple nodes. This is how it looks with Java serialization. So the table is extending a lot, and the ball takes longer to go to the other end of the network. And like I said, it's slow and footprint heavy. So since Akka 2.4, we actually log a warning. Now people at least know that they're doing something wrong. You'll notice that there is no magical like just do this instead in the warning? Well, that's because sometimes you want to take a little bit more development overhead, for example, protobuf, and sometimes you don't. So, for example, with cryo, it's relatively easy to set it up. But it's always a decision of how much pain am I willing to get more throughput, right? So I don't have the answer for you. We would have to talk, well, how much pain are you able to swallow? So here's a very naive, not very naive, semi-naive ping pong benchmark with the Java serialization and without. So without the serialization, a ping pong goes back and forth below a microsecond, right? With the serialization enabled, around 25, right? So that's pretty painful. But let's see how we can do the actually, how do I put this? Let's do something that's already good. It's not the best thing we can do, but it's already pretty simple to set up. And I mean the cryo serialization. So cryo is pretty good because it comes, well, at least the this library, so Akka cryo serialization, comes with a bunch of presets for the Scala collections, right? Because that's what you're going to be sending around. And configuring it as simple as, well, you get the plugin, you register it as an extension, and then you just say which types should be serialized using the cryo serialization instead of the Java serialization. And you could even disable the Java one so it blows up if someone tries to use Java serialization. And I'd actually recommend that. Okay, so as simple as saying serialization bindings, class names, and which serializer. Can I have a quick poll? Who knew about serializer configuration? Okay, that's exactly why I do this talk. Not that many people raised their hands. So you see, it's really that simple. And what's our benchmark now? Well, it's 5 times slower than no serialization, but not 25 times slower, right? Pretty good. And if you really want to, you can go faster, but it will require more coding from you. So why is it actually that slow, this Java serialization thing? So if you have this case class called order, has a bunch of fields, and if we try to serialize it using Java serialization, this is what you get out of. So whenever there's a dash, it means a non-printable character. So it's just the blob that I printed out, well, James Sutherland printed out. And this is how it looks. Quite a bit. And it also includes all the full class names of everything and the field names and everything, right? Very full of information. This is how it looks in XML. So actually, even serializing to XML would be less bloaty than the binary Java serialization, right? Think about it. Scary. JSON would be even smaller, but well, not that smaller. And this is how it looks in cryo. So as you can see, because it doesn't include the names of the fields, but it does include the names of the types. It tries to shorten them a little bit. But you see, it's somewhere in the middle. It includes some information about the object, but not all of it from the type-wise approach. Okay, so, and it's even worse if you try to use Java serialization with any kind of system that needs to get back to this object in 5 years' time. So any kind of persistence systems, right? Because that means that you will try to evolve the schema, and evolving a schema is not very pleasant with Java serialization. You can go around it. There's this serial version UID fields, but it's not very pleasant. So if you're trying to do any kind of persistence with binary formats, then please do decide either for protobuf or for thrift, something that has built-in schema evolution. And yeah, it's going to be a bit more painful than just click and it works. But you kind of pay upfront a little bit of pain, and then you have 0 pain once you evolve the schema. With Java, you would have first 0 pain, and then a world of pain, right? So it's a trade-off when you pay the price. And the usual trust no one slide, because I shown you a benchmark. Never believe in anyone's benchmarks, right? You should always benchmark yourself and verify that I'm not completely lying to you. If you're benchmarking anything in Scala, then please do use the SBT JMH plugin. And JMH is this benchmarking tool from the Oracle guys that they use to benchmark the collections, etc. So it's a very good benchmarking tool. And then profilers, and if you want to go really hardcore, then go with perf and look at the actual assembly that's being printed. But again, trade-off of how much pain you're willing to take to get a good benchmark. Okay. So different topic about letting it crash, right? That's both the Erlang and the Akka motto. We just say let it crash and it'll recover. But there's one fine detail about it that sometimes people forget, or they use maybe the words failure and error interchangeably, whereas we don't think it's the same thing actually. So an error is something that's expected, and the error happens, and I can react to it. And then there's a failure, which is basically, wow, I didn't completely expect that, something is really blowing up in the system. So to make it maybe more exemplified, so let's say you have a vending machine, and inside there's some hierarchy of actors trying to handle your request to get some drink out of the vending machine. And money comes in, and then there's actors responsible for each row of cans or something. Let's just imagine it is like that. Probably isn't. But now an error is if there's some validation and it sees, oh wow, that's not enough cash for the product you wanted to buy, right? So that's an error, at least in our terminology. And the error goes back to the end user, right? Because they can react to it. They will insert more money and then they'll get the drink. However, if the validation passed, we try to get the, Coke out of the vending machine, and actually this fetcher arm thingy blows up, or doesn't react or something. So that's actually a failure. And where is the difference? So the difference is in where we report this, right? So an error, we report it to the end user. We say, well, you can't get this can of Coke because something. But the actual, internal error message, failure message, we send it back to whoever is supervising that machine, right? Because they can actually repair the machine, and the end user can't, right? So it's this difference of who can do something about the problem. So about failures, operators can do something about it, supervisors can do something about it, but not the end user, all right? A little bit fuzzy, but I hope the example is helping. We have a question. Right.
Are you supposed to report an error to the user? Otherwise, he will be just waiting for his scan to appear.
Yeah.
To no avail.
Yeah, that's a good example. So everything completely blows up, but what does the user get? Well, usually at least there should be in many operations like that, there should be some timeouts, right? And a timeout then reports back with a generic error message to the user that, I don't know, something went wrong. Even if you have no idea what went wrong, and you don't want to tell the user that, the mechanical arm 50 is broken or something. This you want to know in your supervision hierarchy, and maybe notify, in a very real life case, you would maybe shoot a notification to a monitoring system, etc. But it's not the same information you give back to the user. I hope this addresses the question.
So basically you propagate it, the way is to propagate the error,
yeah.
Convert the unrecoverable failure to
yeah.
error.
Yeah, exactly. Because you do want to tell something to users, but usually it will be then something not very useful, like, well, error, sorry. Maybe just print an error message that says, oh, I'm sorry, we will fix it. Okay, so Backoff Supervision, that plays again into the same topic. So you have supervision, and supervision takes care of, for example, restarting an actor if it fails, right? But Backoff Supervision is something we recently discovered during working on Akka persistence. And the case is that you need to give a little bit more breathing time to a system before you recover. Otherwise, you'll be basically DDoSing your own system. So here's an example. So yeah, we want to let things crash, but that doesn't mean let them crash and then let them crash even harder, right? We want to let them crash and recover, right? That's the second part of the idea. So here's the problem case. You have some kind of database, doesn't really matter what, and you try to persist some kind of messages to it because it's a persistent actor. So the way persistent actors work is they can store events in a data store, and then once they fail and recover, they go to the data store and recover their state from the past events that they were persisted. So the current model we have is if the data store is unavailable, we always stop the actor. So it doesn't restart automatically, like any other actor would normally do. So here's why we don't do that. So this is not what happens, but this is what was happening at some version while we were developing this in 2.3. So the normal actor behavior is if it fails, it restarts, right away. And here's the problem with that. If the data store is unavailable, we fail, we restart, we want to replay fails, so we fail, so we restart, we try to hit the database, and it bounces back and forth all the time. So if this is one actor, this maybe wouldn't be such a bad thing because we try to recover as fast as we can, but it doesn't happen with one actor. It's in your entire cluster. We're hitting the, for example, Cassandra cluster with this recovery mechanism, and then the entire bigger cluster is trying to hit the data storage cluster with all these recovery messages. And maybe the data store is still not up or trying to get up, and we're basically DDoSing it, causing the system to have even more trouble than not. So this is why we do the stopping, independently of, if we could just replay, because we don't know. And then we have someone called the Backoff Supervisor. So the Backoff Supervisor is basically someone on the outside of the supervision hierarchy, but kind of doing the same thing, with the difference that each restart of the actor is basically timer-based, right? So we try to restart after immediately. Then if it failed, we try to restart after a second. If it failed again, we try to restart after 3 seconds, etc., etc. We give it more and more breathing space to get to a recovered state, and then we'll recover. And that's something we've implemented for you. You can just configure it, so you just need to be aware that such a thing exists and that you maybe sometimes be needing it. And it's not only about some database failing. It could be also maybe you're hitting some, exceeding some SLAs and hitting some external services. You could do the same thing, just let it crash and then let the supervision, the Backoff Supervision kick in so you get back after a short while. Okay, that's a funny one. So when you start designing using actors, you basically translate every method, what would have been a method, to a message, and then you have a very long list of messages like that. So this is not yet long. Long would be maybe 10, 15 messages. Depends on your code, right? But this basically is the same problem as JavaScript people have with this pyramid of doom, only that we don't have a pyramid of doom because everything is a message, so it looks flat, but effectively it's the same problem. Right? Everything is a message, everything comes back to the receive block. So when you think about it and try to model it more explicitly, for example, the receive first is awaiting for instructions. Okay, so what is awaiting for instructions? It's termination handling or 1 or 2 cases doing something, right? And then once you get some kind of message, you transition to another part of the protocol, which is making things. Okay, what is making things? And you see you start modeling it as a finite state machine. And it reads much nicer, and maybe you can even test it independently, etc. So basically, you're gonna get some kind of finite state machine. If you really want to, there's a DSL that helps writing finite state machines. So here you say in what state and what should be happening. and it can include data. So here the second thing is actual data. So you don't need to resort to mutable value variables in the actor. You can just pass it along in the second parameter if you want to. Okay, so that's the last topic. Cluster convergence. So before I start, who has been using the cluster? Who knows what convergence is? Yeah. I don't mean to say that's bad that you don't know, but it's probably not as well exposed in the documentation as it should be, so people don't realize what it is. So in order to have any kind of membership change, we have to have convergence in the cluster. And convergence basically means that everybody agrees that they see the same state of the cluster. So here's how it looks in a state diagram, but here's how it looks on a party. So you have some seed nodes. So seed nodes are the nodes to which you go to the party to join the cluster, right? You know their addresses. And the guy with the funny hat, that's the current leader, right? So leadership, it's not a very special node. It's just that, yeah, we have some leader, and if it goes down, the leader becomes the second oldest in the cluster. So we have a node called Kurt. It tries to join. Then the nodes, I don't know if you see the K here. So everybody gets the notification that Kurt wants to join. And once everybody knows about this node, we move it to up. Right? So the idea is that everybody knows about something, and then we make a decision on it. Okay, so now he's part of the cluster. So that was convergence, basically. But now if you have a situation where Kurt is unreachable, so we can't communicate with the node, and someone else tries to join, we don't have convergence, because convergence means everybody knows. But we can't tell this unreachable node. So not everybody knows, and we can't make this up decision. So there's an improvement in the cluster that you can enable, and that's allow weekly up members. And that allows actually new nodes to join even if there's someone unreachable, right? So if you have situations like that during a cluster partition, because that's a cluster partition basically, you need to add new nodes, you do want to enable weekly up members. And that then both allows the member to join as a weekly up member, and once the unreachable node comes back, the new one will be moved to a proper up state. So we still follow the same protocol, it's just we allow nodes join earlier. Okay, and here's the opposite of leaving a cluster. So say you have a party, that's Bill having a birthday party, and he says, I'm gonna go home. Basically calling cluster leave self, right? And then you kill the JVM. Right away, next line, system exit. Now the problem is, because quitting is also a asynchronous operation, if you killed the JVM before anybody heard the message, then no one heard you saying goodbye. And they'll start worrying, like, where's Bill? And failure detection triggers, etc. Where you meant it as a proper nice leave, but it wasn't a nice leave because no one heard you leaving. So then failure detection triggers, and they move the node to unreachable, right? So, and from unreachable, someone can decide to call it down. And there's ways to configure how downing works, but basically, once a node is down, and it comes back, we will refuse talking to it. So you're already dead. I will not talk to you, even if it's, well, from your perspective as an operator, you're looking at this cluster, the node came back and should be fine, but it isn't because the cluster already decided that the node is dead, and it could have some inconsistent state, right? And we don't allow members to come back then. If you actually don't care about consistency in that sense, maybe you shouldn't be using stuff that requires a single writer principle. So Akka persistence requires a single writer principle, but for example, Akka distributed data doesn't. So there's ways around that if you don't care about consistency in that sense, but it changes your availability model. Okay, we're running out of time. So Akka is a toolkit, I talked about it. You can pick and choose small things from it. And also, you should be using the least powerful abstraction that does the job for you, right? Sometimes a future is enough, but not always, right? Because futures don't do distribution. So they have less power, but they're easier to work with, right? And if you go with actors, you get a lot of power, they do distribution, they do failure recovery, etc. But they're a bit harder to work with, right? So it's this opposite, and here you have power, here you have constraints, and they're always pointing in opposing directions. So think about what you're trying to use. A nice middle ground is actually Akka streams. So if you haven't seen Akka streams yet, give it a look, because it's a statically typed way to kind of explain a processing pipeline, but it's static, right? Actors can be very dynamic in their lifetime, and streams are very static in how the data flows through the system. So again, it's a trade-off. Okay. Okay, happy hacking. This is where you can reach out to us for random chatter or just feedback. And of course, we do take contributions, and if you want to help out, the best way to get started is to look for the community contrib or the small tickets. And just ping the ticket that, hey, I want to work on it, and I'm happy to help out you contributing us. And there's also chat rooms. So the Akka is for actually using Akka, if you're writing an app and want to know something, how to do something with Akka. And the Akka/dev chat room is for actually developing Akka, if you're trying to contribute a feature or something like that. Okay, here's some, that's our commercial offering, if you want to have a look. This is what keeps us alive, basically. And that's my last slide, which is again from the Zen of programming. So thank you very much.
We have time for 2 or 3 questions.
Oh, we have one here.
Is it possible, or will it be possible to use distributed Akka streams?
Yes and no. So, with Akka streams, we have 2 layers. One is the DSL, and the DSL is actually a lifted representation. It's basically like an AST. And then we have a second step, which is actually materializing the thing, so making it run. And the Akka streams implementation on Akka is not really targeting the distributed case. What we are targeting is basically doing a high-performance back-pressured HTTP server. So that's our use case. But because it's lifted, and basically the guys at Intel who we are working with are focused on the distributed middle wheel-like processing framework thing. So what they do is they take our DSL and they basically just change one line, which is they use the gear pump materializer instead of the Akka streams materializer, and then it is basically distributed stream processing. So with the same DSL, just a swapped engine, you get what you want, basically. So if you want to Google that up, that's Intel gear pump.
Thanks.
One more question.
So, will it be possible to integrate back pressure supervision with existing supervision structure? You know, because for example, right now, if we have Backoff supervisor, there are some problems when it comes to keeping up an actor mailbox and things like that. And do you plan some kind of composing these features into one?
Back pressure with the Backoff supervisor, because back pressure is different.
Sorry, I don't mean back pressure and Backoff supervisor, but standard actor supervision and Backoff supervision.
No, it has to be separate, because the way supervision works is always immediate, and that's really built into the model. So if you need the Backoff supervisor, the way you structure things is different. It's this guy on the outside doing the timers and everything. So we won't be really able to change the existing supervision to do Backoff supervision. But the good thing is you can just edit transparently. It doesn't impact the outside structure of your actors. So that's a mix good and bad, I think. Okay.
Okay, let's thank our speaker once again.
Thank you very much.